Alright, so what we were talking about now was, so we had said that these are the encoders, and then you stack some n encoders like this, okay. Now we were talking about something here. We give them input as x1 and assuming that our input size is 512, this is what we said. Okay. Now, so this is 512. The problem was here. What was the problem? We said that every word has its own path. So every word takes its own path and is processed in parallel. Okay. Now, can you process all these things here in parallel? Of course. Where is the sequential, inherently sequential thing? Exactly, right? So if this is encoder 1, encoder 2 cannot process until encoder 1 is finished. Okay. So in this way it is still sequential. So so this line is still sequential. And you have got no way to parallelize this because encoder 2 will have to wait for the output of encoder 1 to be able to process anything. Next, we were talking about something here. Okay. All these are parallel paths. What is lost? Right. Without the notion of sequence, right, this becomes a bag of word. You process x1, x2, x3 all the way until x512, or you process any permutation of it, they are going to give me the same thing. Do you visualize this? See, every thing takes its own course, okay, and it does not really matter whether you process x1 here or x1 here, it is going to give me the same thing. Same mathematical operations will happen, same numbers will be get multiplied and so on. Now what happens here? So in order to bring back this notion of sequences, the authors use something called positional encoding. So, now this, see, I have tried a lot to, this thing remains the most elusive for me. This, I am not sure if this is the paper that has introduced this idea, but this is very, I mean, this is the idea that probably makes this whole thing work, at least in 2017, right. Today people are talking about, so this has opened a different area of research in itself. What is the job of positional encodings? We have not seen what are they, but what might be the job? It should be somehow able to tell this whole machinery that x1 comes before x2, x2 comes before x3, and it should also be also be able to capture this fact that x1 is actually very far away from x20, for example. So the distance between x1 and x2 is more than the distance between x19 and x20, or x10 and x20. Okay. So, and the way they do it, this is awesome. So later later research, people say you don't really need to put the positional encodings the way they do this in transformer paper. Some say, so for example GPT, it does not fix any positional encoding, it simply learns them. There are some papers that talk about that you don't need positional encoding at all. Okay? So this is the state of deep learning where you don't really have a concrete set of idea what should be done, what is the right thing to do, right? Most of the times you are in these two arenas. One thing that simply does not work for you, or one thing that you simply don't know how to make it work for you. Another one is it works. Why it works, we may or may not understand that. Okay? At least for me, positional encoding has that same status. They work, but I don't feel at home with why should they work, and to me this is the super genius of the authors to be able to come up with such things. I am not sure if this is the first paper that introduced this. I should have done this before this class, but anyway. So now talking about positional encoding, so let me write so I am writing this from the paper itself. What they do. So what they do is that they don't feed X1 itself. Positional encodings are coming from here now. So P's are coming from here, I's are coming from here, and what you actually input is Xi tilde, which is original Xi plus Pi. So this is the Pi. Now this should make sense. I'll fix it. So D is basically D model, and D model for transformers. So D model is 512. This number 512 is basically so this is called the dimension of the transformer itself, which is basically the dimension of the words the transformer is playing with. So remember, we had said X1 is 300 dimensional. For original transformer, it is 512 dimensional. So the embeddings are not 300 but 512 dimensions, equal to D model. Okay. Now, so what will be the dimensions of my Pi? If this guy is 512 cross 1, then this must be 512 cross 1 as well. Now, what are these things? And before that, so in today's class I plan to do just this, but I don't have that much time. So, right. So, how do they capture? So, why do they capture positional embeddings? It's not at all clear. Second, what else we can do? How can we capture this notion of positions? Do you see where are transformers lacking? How many of you are able to visualize this? That there is no inherent notion of sequences here. Is this fine? Right. But sequences are important because otherwise any permutation of these 512 words is going to give me the same output. So without positions, that's a big deal. At least initially in 2017 people were thinking it to be so. Even today there is no clear strand of research that says whether you need positional encodings or not, and if you need, which ones are the best. Okay. As far as my knowledge goes, now, so this is 512 cross 1, this is 512 cross 1, this is our simple thing, but since we always write the dimensions of our vectors, so just do it once more. Now, all these are 512 cross 1, so my first encoder is also going to take input of size 512 cross 1 like all other encoders. Okay. Now, see, people talk about very other possibilities. What can be other possibilities? For example, can you do things like one hot encoding of position? Like with x1 you can say, what will you add to x1? Now there is. So people don't even unanimously accept that plus is the best thing to do. You could also concatenate, okay, but for the variants that we will see, plus is used. So now tell me, what was the question? One hot, right? So how can one hot representations of positional embeddings help me? So in that case, what will they be? For x1 it should be 1 and then remaining 511 zeros. For 2 it should be 0 1 and then remaining 510 zeros and so on. Okay. So to me this looks fine. I mean, first of all, I have no idea how should these guys look like, but at least these one hot embeddings, they look reasonable to me. But it turns out they are not good. Why? Which probability? No. We are just talking about in terms of positional encodings. We are not even going there up. See, how do word embeddings look like? Anyway, whatever they look like, if you add, so if you do this positional embeddings, okay, one hot embedding, what is the norm of x, what is the norm of P1? What is the norm of P1? Norm means modulus of this vector. 1. What is the norm of P2? So P1, so the distance between P1 and P2 is same as distance between P1 and any other vector, because norm of all these guys is 1. So it basically does not change. Right. So what else we can do? No, sorry, norm is 1, but what is the distance? Right, distance is different. Distance is root 2. You will have 1 square coming from here plus 1 square coming from the other one. You will take root of that, so that is root 2. So the distance between all pi's for, so distance between pi and pj for any I and j except I not equal to j, that is going to be under root 2. When I is equal to j, that is going to be 0, because the distance with itself is 0, right. So one hot, it turns out, is not a good idea. Anything else that we can do? Hmm. 003. Okay, so what we are saying is, that's a good one. So for P1 you said 1 and everything 0, right? For P2 you, so basically I will write, basically instead of P2 I will write P20. So it is 0, at 20th position you have 20 and rest 0. Huh? What will be P512? And what is wrong with this? So what is wrong with this? What might be wrong with this? See, in the end these are mathematical magnitudes. Norm of this vector is 1, but norm of 512 is much bigger than this one. So are you adding this artificial norm to the vectors? 1, okay. What else? See, I mean, we have not done computer vision that much, but in vision if you see, what are the values of pixels? RGB, whatever it is, but the values will go from 0 to 255. Now, if we are talking about just, so I'll take a little bit digression. So if you talk about this pixel 0, let's talk about just black and white. What is pixel 0? 0 intensity, so that is black, okay, because 0 intensity of the pixel. What is 255? Maximum intensity, so as white as you can get, and everything in between you will have a grayish flavor, okay. Now this is mathematical, in the end everything has to be numbers, right. So this is a number 0, this is a number 255, but conceptually if you think, for computer vision they are intensities. So at least this should not change, that this mathematical number assigned 255 will in a way change your math compared to this 0 or 1 or 2 or 3, okay. So what do you do here? In this case it's a simple hack. What you do is you divide every pixel value by 255. So at least try to restrict between 0 to 1. Even there is a kind of ordering which I would prefer not to have, but still it's much better to have a range between 0 to 1 compared to 0 to 255. Same kind of things are happening here. Your one norm has value, I mean one positional encoding has value 1, another one has 512 or 20, right, and they are very different. Moreover, apart from just this fact, you also have problems here. So xi's are typically of this type, 1.239 minus 0.08342. So these vectors, right, the numbers inside this x1, they are, so xi's typically look like this. So they are small numbers, usually they are not big numbers. So it can be minus 0.081, 2.8962, minus 1.003 and so on. So these numbers are usually not that big. Now suddenly you start adding 512, right? So I mean, does this make sense, or you wanted to say everywhere there should be 20? You wanted to say just the earlier one? You wanted to say the earlier one, or everywhere I should add 20? Why? Exactly, right? So, you know, when you start adding these big numbers here, what will happen? Your original word embeddings, they will lose their significance and it will be dominated by this term pi, which we are artificially adding. right? So the original significance will be lost. And that's why I say the authors have done it beautifully. What they do is they add this. What are the properties of these? Because they are sine cos, they can lie between -1 to 1. Okay. One hot vector
उसके पैरेलल में 1 है तो उसका सिग्निफिकेंस दिखा रहा है कि ये यहाँ का x1 वर्ड है.
So you want to add or concatenate?
नहीं, concatenate.
So concatenate means one comes here.
नहीं, 512 cross 2 नहीं बना सकते.
That is same. So what we are saying 512 cross 2, that is same as 513 पे 1. Okay. Machine is agnostic to this, whether you take this vector here or whether just write it here. Right, but this does not work for the other reasons that we had discussed, because norm is, I mean, just the properties of position embeddings themselves is not satisfied, because the distance between any two PIs is the same. Okay. Now, the way this looks like, okay. Now, if you see here, what is I? So I is for my ith word. So this is my word, and this whole thing goes across the word. What are these guys? So let's try to compute what is the, so Pi. If we start with 0, let's say x0, P0, what is P0 going to give me? The first word. Now it is much better if I, just a second. Something like this. Okay. So when you start, let me see if I can. So this is how your, so they go between -1 to 1, okay. And for the first word, why we have just, zeros and ones, why? So, see, I don't want to switch there again. Have you written that? What was that? It was sine of 1 upon 10,000 to the power 2 into 1 divided by d. Okay. So, denominator does not matter because I is 0. So this is just for 50 words. Okay. So 0. Now this one will alternate between, so for sine it is 0, then next is cos 0 is 1. So 0 1 0 1 0 1, okay, for the 0th embedding vector. Next one, what happens? You see there are changes, but later we still start seeing 0 1 0 1 0 1. Why so? Because your denominator is really huge, and whatever the term inside, that becomes close to 0 again. But as you go far, you can see these things are far away. Okay. Now the important properties of these embeddings. So this is my first positional embedding vector. This is what I am going to add it to the, what are the dimensions of this position embedding here? 128, and we were talking about 512, okay. So this is my P0, second row is my P1 and so on, okay. Now it turns out that this particular function has all the properties that we were looking for. What is it that we were looking for? So distance. Now distance between this and this is actually small. In fact, the distance between any two neighbors is small. Why do you think so? That we can see just by looking at this figure. I mean, this heat map is nothing but these values. So the darker towards the maroon, that means you are closer towards -1. If you are almost white, you are closer to 0, and if you are blue, you are closer to 1. So where is the difference more between the 0th position embedding versus the last one? Yes, Euclidean distance. What is the Euclidean distance between these two? Compared to between this one and this one? See, if at each position your numbers are similar, then your distance will be lesser, right? And if at the corresponding positions your numbers are very different, then the distance will also be different. I mean more. Why? Because you take, so how will you compute the distances? First position minus first position of this taken square, this one minus this taken square, add all these things and take square root. That same distance, x1 minus x2 square plus y1 minus y2 square under root. You do it for 128 dimensions, okay. So that gives you this desired property that we were looking for. What was that? Distance between first and 40th should be more than the distance between 0th and 20th. It turns out they respect this thing, okay. They also don't violate this other thing. What was that? So this distance they capture. What else? One more thing that these embeddings respect is, let's say if you are talking about positional embeddings at position number 50, right? The distance between 50 and 51 is same as the distance between 50 and 49, and we would want that, right? The distance between 50 and 52 is same as the distance between 50 and 48. So it is symmetric both sides. So the distance of positional embedding 60 and distance of positional embedding 40 from 50, they are both identical, same, okay. So they come up with this, and you can plug in the formulas and keep on generating that thing, okay, and it turns out it works for them. Now what am I missing here? Sorry? So magnitude, it doesn't explode like these people, because what you are doing is you are still adding just small numbers, and you are actually adding very small numbers. Now okay, the lectures by Mitesh Khapra, they have a very good discussion on it. Okay, so I'll seriously recommend that course for you people. So go and, I think I have covered what is required, what is intuitive, but if you want to dwell more, he talks a bit more about it, because he will give you these numbers between. So what will be P0? This is 0, 1, 0, 1, 0, 1. What will be P1? Sine 1 divided by this guy. So keep on computing this again. This will not be 0, this will not be 1, but very close to it. What about the next one? This will not be 0, this will not be 1, but it will be more than what you had in case of I equal to 1, because you have I equal to 2. So these numbers change very slightly. So you are incrementally adding a little bit numbers to every embedding, and it so happens that the distance between two very distant positions, that is high, and the distance between any two nearby positions, that is lower. Okay. It turns out that this distance, it kind of increases something like this, okay, but it still increases nevertheless. It will have to in the end flatten out, because your numbers are not going to be unbounded, they remain between 0 and minus, 1 and minus 1. Okay. Questions here now? So sorry, that's what I am saying. So there was a lack of homework on my part. I don't know whether the transformer paper is the first one to introduce this kind of a notion. I think it will be too much to expect them to invent this. So some work should exist, but then I don't know, because this paper is so seminal. So if later, let's say some generations will talk about, let's say they have AGI, right? So this paper will be called the start of AGI era. This is so influential paper. I think I have talked about positional embeddings, and does this make sense to you? See, what was wrong with the transformers the way we were doing earlier? They parallelize everything, okay, and you don't have that dependence on just one vector like you had in LSTMs. But something that was so natural to LSTMs, it was the notion of this sequence, that was taken away by this architecture. Okay. Now you bring it back by adding positional encodings, and guys, it works. I have no idea why should it work, but it does. Yes. देखो, so I cannot answer your question completely, but we have seen P1, the distance between P0 and P1 is lesser than the distance between P0 and P2. That much you can show. And how can you show that? See here, this is 0 1 0 1 0 1. Okay. What is this next guy? Some small changes. Okay. And you keep on taking these differences. So the distance between the first one and second one will be lesser than the distance between this one and this one. No, here this is understood, there is nothing. So, what I personally don't understand is why should this work, but this works, and then the later line of research that shows there are different kinds of embeddings. Some people just learn them, they don't keep these sine functions. Some papers exist that say you don't even need it, but there is no definitive statement that says you need it or you don't need it, or if you need it, then which one are the best. What you can say is that among these one, for this task, this one performs the best. And later papers, so as time has increased, I mean this paper was 2017, people don't use these as frequently as they were using closer to 2017. GPT, for example, learns these. GPT does not keep them fixed. See, if you see these two vectors, or if you take any two nearby vectors, see the distance between them is lesser. Distance means their color coding is very similar, and the color coding, for example, here is very much different from this one, and color coding is giving me my magnitudes. Okay, this is something you can do by hand. You can do it for a very small size vector. Let's say positional embeddings are of size 4, and then you can do this math. So I think this is all I had to say about positional embeddings. So we have talked about positional embeddings, encoder structure. What remains to be done are three things: layer normalization, residual connections, and masking of attention, and then transformers will be over. I should be able to do in at most 2 lectures. Yes, questions? Decoder is same as encoder with some change. So decoder, some change is there because see, decoder will receive inputs from encoders. Okay, so I mean the last encoder. So there you have this cross attention part as well, because you are attending to vectors from someone outside. So they have self attention, but you also have cross attention in that case, and that's it. Okay. So original transformer paper says use 6. If I am not wrong, BERT says, so BERT has 12 of these. GPT also has 12 of these, but BERT is encoder only model, GPT is decoder only model, and T5 is encoder decoder only model. These are the 3 kinds of branches that we have today, and we will do one of each. Okay, chalo, that's it.